We begin with the basics of functions, basically denotation. So if we have f bracket x equals to 1 over x minus 1, where x cannot be 1, this x cannot be 1 is basically the domain of f, or df. fx, or 1 over x minus 1, is basically the output, or known as the range of f, Rf. So if the domain of f is minus infinity 1 to and 1 to infinity, our range of f is simply following the domain minus infinity to 0 and 0 to infinity. We then move on to composite functions, basically two functions in one. If we have fg bracket x is simply replacing every x with gx, therefore f bracket g bracket x. And there's no condition to exist. The idea is that because your gx is now the input, therefore the range of g must be a subset or equal to the domain of f. Therefore, if we have fx equals to 1 over x minus 1, we know that domain is minus infinity to 1 and 1 to infinity. And if let's say we have gx equals x squared plus 2, we know the range of g is 2 to infinity, and you notice that the range of g is a subset of df. Therefore, fg exists. And because of that, we just simply substitute x with x squared plus 2 in fx. We therefore have 1 over x squared plus 1, where now the domain of fg is the range of g. We then have self-composite functions where we have f's quote-unquote power n bracket x is simply applying f n times, and this is called the self-iterated functions. And there are some patterns actually. So let's say we have f2x equals to x, f3x will simply be fx, and if we have f2015x is simply fx. Similarly, if we have f3x, we have f4x equals fx, f5x equals f2x, and if we have f2015, we know that the remainder is simply 2, therefore f2x. We then move on to piecewise functions, basically multiple functions in a function but for different domains. So let's say we have fx equals to x squared plus 1 between x1 and 3, and x4x between 0 and inclusive of 1. And then we are also told that fx plus 3 equals to fx, therefore f7 equals to f1, and f minus 4 is simply f2. However, if we then add another condition where it is 0 for every other x, therefore f7 equals to 0, f minus 4 equals to 0. We then move on to our f inverse or inverse function, where we have f power minus 1, which is f inverse, alright? So for f inverse to exist, f must be a one-to-one function, where a one-to-one function is basically for every y value or for every fx value, there's only one x value that can get that particular y or fx value. And to test for a one-to-one function, the function must pass the horizontal line equal y equals to k test, where there's only 0 or 1 x solution, aka 0 or 1 intersection point with the y equals to k test. And this k is for every real number. Alright, so for example, if we have fx equals x squared plus 2x, it's a quadratic graph, right? X plus 1 squared minus 1. Therefore, there's no f inverse unless we restrict the domain. So let's say the domain is either x less than or equals to minus 1 or x greater than or equals to minus 1. Basically, x minus 1 is the turning point. So the thing is this, f inverse x exists as long as the domain, the new domain or the restricted domain is a subset or equals to minus infinity to minus 1 or minus 1 to infinity. So it can be minus infinity to minus 2 or 0 to infinity. To find f inverse, just let x be the subject. Alright, so let's say that our domain is now x less than or equals to minus 1. We then have plus minus root y minus y plus 1 and x equals to minus 1 minus root y plus 1 because x must be less than minus 1, therefore rejecting the positive square root. As such, f inverse x equals to minus 1 minus root x plus 1, where we just change x to y and y to x from the second last line. Now the relationship between f and f inverse, we have y equals to fx if and only if x equals to f inverse y, where we have x as the input in our y equals to fx and our output as y. Now if you look at our f inverse, right, we now have our input as our output and our output as our input. And as such, it basically boils down to y becomes x from f to f inverse and x becomes y for the same thing. In fact, vice versa. Alright? Now, one is that f is actually a reflection of f inverse x in the line y equals to x and vice versa. And the number two is that the range of f is now the domain of f inverse, and the domain of f is now the range of f inverse. Another thing, f inverse f equals to f inverse x equals to simply x, and f inverse a equals to b would mean that fb equals to a. If we have the composite function fgx equals to k, gx is simply f inverse k. However, one thing to take note is that if you have fg f inverse x, it is not gx, alright? Because f inverse or f inverse f only cancel out when they are adjacent.